Okay, so question is show 0 comma 1 is not compact in R comma D where D is usual distance. Okay, we will show that this interval is not compact. That means we will find an open cover which has no finite subcover. Okay, so what we will do, let G is collection of 1 by n comma 1 such that n is in n. Okay, so this is a collection of open subset of R. So our step 1 is A, which is 0 comma 1 is contained in union of 1 by n comma 1 where n is in n. So we show this. Okay, so to show this statement, so what we will do, let x belong to A. So that means x is greater than 0. That means 1 by x is also greater than 0. So what we are trying to do is we are trying to find an element. We will try to prove that x is in some interval like this. Okay, that means x is ahead of some 1 by n. So for that purpose I have taken the reciprocal. Now we know by Archimedean property there exists some n naught is in n such that 1 by x will be less than 1 n naught, and that would mean 1 upon n naught is less than x. Alright, so we found an interval like this where x can belong. So that means our x belongs to 1 upon n naught comma 1 for some natural number n naught. So therefore A is subset of the union of 1 by n comma 1 where n is in n. Okay, pretty simple. So we take any random x, but these are some reciprocal. So we try to take the reciprocal and then we try to apply Archimedean property and we get a statement of this form. So because of this we can say G is an open cover for A. But the thing is that, so step 2 we will show that G has no finite subcover. Okay. Okay, so we got an open cover. Now it has no finite subcover. Why? So step 2 is show G has no finite subcover of A. So suppose not. That means that is there exists some n1, n2 up to say nk belonging to n such that A can be covered by 1 upon n1 comma 1 union 1 upon n2 comma 1 union with union of 1 upon nk comma 1. Suppose there is a finite cover. Okay, so what we will do, we want to make this contained in some bigger interval. So we will choose the biggest of all element like 1 upon n1, 1 upon n2. We want to choose the biggest among all. So that is done by choosing n naught is minimum of n1 up to nk. So that means n naught is greater than or equal to ni, right? And that means 1 upon n naught is less than 1 or equal to 1 upon ni. So we have 1 upon ni somewhere here and 1 upon n naught somewhere here. So naturally it implies 1 upon ni comma 1 will be contained in 1 upon n naught comma 1, and this is happening for all 1 I1 to k. Right, so each interval here is contained in 1 upon n naught comma 1. That implies A is contained in 1 upon n naught comma 1. Alright, so now we want to get an element which is in A but which is not here. That will give us a contradiction. Okay, how we did that? We got the minimum. We just took the largest among all, this reciprocal. That is done by choosing the minimum of all denominators, and we get a relation of this form. But we know that the range 1 upon n naught comma 1 and A is starting from 0. So there is definitely going to be some element over here. So something which is before 1 upon n naught. So by taking the same idea, so what we will do, we will know that n naught plus 1 is greater than n naught. That implies 1 upon n naught plus 1 is less than 1 upon n naught. But 1 upon n naught plus 1 belongs to A, and 1 upon n naught plus 1 does not belong to 1 upon n naught comma 1 because it is before 1 by n naught. So therefore we get a contradiction. Hence we can say that this type of finite cover is not possible, because whenever we find a finite subcover, we will get an additional element in A which is not in this set. So therefore A cannot be covered with finite open intervals. There is an open cover which cannot admit a finite subcover. Hence A is not compact. Okay, thank you.